In this video, we're going to take a look at something called differential equations. These are really powerful mathematical tools. We'll examine what they are, what their solutions look like, and why they appear everywhere. A differential equation involves an unknown function and its derivatives. Examples include equations like dy dx plus 4y equals the cosine of x, or y double prime plus 16y equals 0, or y prime equals 0.1y times 100 minus y. When we solve a differential equation, we're searching for a function as our answer rather than a number. Differential equations are the mathematical language of change. They describe how populations grow, how objects move through space, how chemicals react with each other, how water drains from a tank, and even how your medication can disperse in your bloodstream. Let's take a look at some important vocabulary related to these equations. We classify differential equations by their order. The order of a differential equation is the highest derivative that appears. So in our previous examples, dy dx plus 4y equals cosine x is a first order differential equation. So is y prime equals 0.1y times 100 minus y. Only the first derivative of y appears in each of these. However, y double prime plus 16y equals 0 is a second order differential equation because the highest derivative appearing in it is the second derivative. A differential equation is linear if y and any of its derivatives appear only to the first power, are never multiplied together, and are not placed inside other functions. Going back once again to our previous examples, dy dx plus 4y equals the cosine of x is a first order linear differential equation. Y double prime plus 16y equals 0 is a second order linear differential equation. Y prime equals 0.1y times 100 minus y is a first order nonlinear equation because y is multiplying itself and would eventually be raised to the second power if we distributed it. We'll see as we learn to solve differential equations that their order and linearity give us important clues about the solution methods we might use. You've probably figured out by now that in order to solve differential equations, we're going to have to take some antiderivatives. You'll recall that antiderivatives introduce arbitrary constants. An nth order differential equation then is going to involve up to n constants. We're going to define the general solution to a differential equation as the family of functions, including the required number of constants, that solves the equation. Let's take a look at an example. Let's verify that the function y of t equals c1 times the sine of 4t plus c2 times the cosine of 4t is a solution to the differential equation y double prime of t plus 16y of t equals 0. So the first thing we can do here is let's figure out, given that y of t is c1 times the sine of 4t plus c2 times the cosine of 4t. Let's take the second derivative of that. So the first derivative is going to be 4c1 times the cosine of 4t. And then we'll get minus 4c2 times the sine of 4t. And then we're going to take the second derivative. And that's going to give us negative 16c1 times the sine of 4t minus 16c2 times the cosine of 4t. We're now going to put that into our differential equation and see what happens. So y double prime of t plus 16yt becomes negative 16c1 times the sine of 4t minus 16c2 times the cosine of 4t plus 16 times y of t, which is c1 times sine of 4t, plus c2 times the cosine of 4t. So hopefully you can see what's going to happen. That gives us negative 16 c1 sine of 4t minus 16 c2 cosine of 4t, and then distributing the 16, we get plus 16 c1 sine of 4t plus 16 c2 cosine of 4t, and that does in fact equal 0 because the negative 16 c1 sine 4t and the positive 1 cancel each other out, and the same is true for our cosine terms. So we get 0, and we have verified our differential equation. We have verified that this is in fact a solution to, or is in fact the general solution to our differential equation. While we don't at this point know a lot of the techniques we'll use to solve differential equations, there's a reason, there's an entire course dedicated to solving them. There are some that we can solve, and this is an example of one. So let's see if we can find the general solution to the differential equation y prime equals 1 plus 2 over the cube root of t. Notice that if we take the antiderivative of y prime with respect to t, we can do the same on the other side. Well, the antiderivative of y prime with respect to t is just y of t. On this side, I'm going to rewrite this as 1 plus 2 times t to the negative 1/3 power. And then we know by our rules of antiderivatives that y of t is going to be equal to t plus 2 divided by, when we add 1 to negative 1/3, we get 2/3. So we'll have 2 divided by 2/3, t to the 2/3. And then we're going to add on our constant. And we'll tidy that up. Y of t is equal to t plus 3 t to the 2/3 plus our constant c1, because this is a first order differential equation. Now, one thing to note is that y of t is defined for all real numbers, but y prime is not. So this is a solution for all t that are not equal to 0. And the reason for that is that if you look back at our original differential equation and you attempt to plug 0 into that, it is not defined at t equals 0, which means that we have to eliminate t equals 0 from the domain of our solution in order for it to be a solution to the original differential equation. We've taken a look at how to find a general solution, but sometimes we don't want a general solution, we want a specific solution. In that case, we're solving what's called an initial value problem, and we need to be given some specific values that will help us figure out the values for the constants. So let's see if we can solve the initial value problem. U double prime of x equals 4e to the 2x minus 8e to the negative 2x, given the initial conditions that u of 0 is 1 and u prime of 0 is 3. So bear in mind that our goal, anytime we're solving a differential equation, is we're looking for a function. We are looking to find a function u of x that satisfies these conditions. We can start with taking an antiderivative. So if we take the antiderivative of u double prime of x with respect to x, that is the same as the antiderivative of 4e to the 2x minus 8e to the negative 2x with respect to x. The left-hand side of that is going to be u prime of x, and that is going to be equal to, taking the antiderivative of 4e to the 2x, we get 2e to the 2x, and then the antiderivative of negative 8e to the negative 2x is going to be positive 4e e to the negative 2x. And then we have to remember that we need a constant. However, we know that u prime of 0 must be 2 times e to the 2 times 0 plus 4e to the negative 2 times 0 plus c1, and that is equal to 3. That tells us that 2 times e to the 0, which is 1, plus 4 times e to the 0, which is again 1, plus c times 1, or plus c1 is equal to 3. So that's 6 plus c1 is 3, yielding c1 is equal to negative 3. So now we have a more specific formula for u prime of x. U prime of x is now going to be 2e to the 2x plus 4e to the negative 2x minus 3. Our goal, once again, is to find u of x, so we antidifferentiate again. The antiderivative of u prime of x with respect to x is going to equal the antiderivative of 2e to the 2x plus 4e to the negative 2x minus 3 with respect to x. On the left-hand side, we have u of x. On the right, we're going to get e to the 2x minus 2e to the negative 2x minus 3x plus another constant. But we know that u of 0, which is going to be e to the 0 minus 2e to the 0 minus 3 times 0 plus c2 equals 1. That is 1 minus 2 plus c2 equals 1, which gives us that negative 1 plus c2 equals 1. So that c2 must be equal to 2. And so we finally know that our solution to our initial value problem is that u of x is equal to e to the 2x minus 2e to the negative 2x minus 3x plus 2. Let's summarize everything we've covered here. First, we know that differential equations are equations that involve both functions and their derivatives. We can use them to represent how quantities change and also to model a number of real-life phenomena. When we find the solution to a differential equation, we're looking for a function rather than a quantity or a number. Differential equations are classified by their order and their linearity. The general solution to a differential equation gives us a family of functions, and those are going to include some constants. Whereas an initial value problem involves finding one specific member of that family using some initial conditions.